So welcome back, Level 2 Physics, and our continuing on with our direct current in circuitry. We're now looking at electrical current, which we briefly touched on in the last lesson. So this lesson has 4 learning objectives. 1, to define current as the rate of flow of charge. 2, to identify electrons as the charge carriers in electrical circuits, reinforcing what we saw in the last lesson. And identify, use, and explain the equation I equals Q divided by T. And finally, identify, use, and explain the second equation I equals never. So continuing looking at electrical charge, protons and electrons both have electrical charge, protons being positive and electrons being negative. Charge is measured in coulombs with the unit C. And 1 coulomb of charge is equivalent to a large number of electrons, 6.25 billion in fact, and there it is as a number. And finally, charge has the symbol Q. So now let's look in more detail at electrical current. So current is the rate of flow of charge, or in other words, how much charge flows through a certain point at a certain time. And current is measured in amps or amperes. 1 ampere is equal to 1 coulomb of charge passing through this single point every second. So if you can think of the analogy of a river, it's the amount of, say, water atoms passing a particular point in that river every second. And current I equals charge Q divided by time taken. Or in other words, I equals Q divided by T. So there is our first reaction, first equation for today. So let's now have a look about what's happening in the wire. So electrical charges flow easily in metallic wires, as in metals there's lots of free electrons which can move when a voltage is applied. Okay, if there's no electrical field, it means that these free electrons move about randomly because you need an electrical field in order for the electrons to have a force to act upon them. And once you have a force, they start moving and accelerating. So when a voltage is applied, the electrons feel an electrical force and they drift in one direction. So here's a diagram that illustrates that. So here we have an electron, which is now, when a voltage is applied, having an electrical field being acted upon it. Now notice the electrical field is in the opposite direction of the movement because obviously it's conventional current. So it's going from plus to minus. So current is going from plus to minus. Therefore, the electrical field is going from plus to minus when you're considering a positive charge. However, the velocity, the drift velocity, is going in this direction because obviously the electron being negatively charged is going towards this direction because it is positive. So here's a few questions. So you have 10 coulombs of charge passing a point in 5 seconds. What is the current? And here's the equation we're going to be using. I equals Q divided by T. So pause the video now, think of an answer, and come back and we'll go through it together. So welcome back. So the equation, of course, is I equals Q divided by T. Okay, I equals Q divided by T. Q in this example is here. T, of course, is here. So it's simply going to be 10 divided by 2, which gives you 5 amperes. Okay, that's the answer to the first question, 5 amps. Next question, a current of 3 amps flows for 10 seconds. How much charge flows past each point? So pause the video now, come back in 5 seconds, and again we'll go through it together. So welcome back. So we have a current here. We have a time of 10 seconds. So we're trying to find Q. So we need to rearrange the equation. So Q becomes I times T, and then we plug in the numbers. So it's going to be 3 times 10 equals 30 coulombs. And that's your answer. And the final question, how long will it take for 100 coulombs of charge to flow past a point when the current is 2 amps? Again, pause the video now, and we'll come back in 5 seconds. So welcome back. So again, look at the variables. We have a charge of Q, 100 coulombs, a current of 2 amps. So again, you're simply trying to find out the time it will take, how long. So rearranging the equation, you get T equals Q divided by I, and it's simply a matter of plugging in the numbers. Okay, so Q in this example is 100 and I is 2, so the answer of course will be 50 seconds. Okay, that makes kind of sense because 100 coulombs is a hell of a lot of electrons. Looking at 100 times 6.25 billion electrons, well, it'll take a while, about 50 seconds for that to happen. Okay, so another concept I want to reinforce is the idea of electron drift, which we went through in the previous slide. The drift speed of an electron is in a wire. It can be calculated from I equals never. Okay, so this is the speed or how fast electrons move when a voltage is applied, when you get an electrical force working on these electrons. And I, of course, is current in amps. N is the number of free electrons per meters cubed. E is the charge of an electron in coulombs. And V equals the drift velocity in meters per second. And finally, A is the cross-sectional area of the wire in meters cubed. So if you have a wire like that, then that's going to be the cross-sectional area there, A of the wire. Okay. So now let's look at a problem involving this electron drift. So copper contains about 1 times 10 to the 29 free electrons per meter cubed. Being a metal, that makes sense. And a copper wire has a cross-sectional area of 1 millimeter squared. So what I want you to do in the next few moments is to calculate the drift velocity when 2 amps of current flows. Of course, remember that the equation is I equals never. So pause the video now, see if you can come up with an answer, and come back to watch the answer that we'll go through together. Okay, so the way I'm going to approach this is I'm going to draw a diagram. So here we have our copper wire, okay, the cross-sectional area of around about, 1 millimeter squared. You have a current, conventional current, remember, I equals 2 amps. So that means it's going from positive to negative, we'll call it. So this is going to be the kind of positive part, that's going to be the negative part. And being electrons, the electrons are going to have a certain velocity through the wire, V. Okay, that's what we're going to try and find. Right, so we have the equation, I equals never. Never say never again, great James Bond movie. Okay, so we're just going to substitute some numbers in. So 2, which is the current, equals 1 times 10 to the 29 times the charge on a single electron, which we know from previous lessons is 1 times 10 to the negative 19, times our mystery value V, times 1 to the negative 6, it would be, because remember we want to convert millimeters into meters, standard form. So 1 millimeter squared is going to equal 1 times 10 to the negative 6 meters squared. Okay, so if we rearrange that equation, we have V equaling 2 divided by 16,000. So the answer will become about 0.000012 meters per second, about 8 millimeters per minute. So a pretty slow little movement of electrons at 2 amps. Okay, because 2 amps is really small anyway. Okay, so that's how we use that equation to try and find drift velocity. Okay, so just to finish up, we're just going to fill the gaps, as it were. So I want you to pause the video now and kind of fit the words into the gaps in these sentences, so we have some wonderful notes summarizing electrical current. Okay, so welcome back. Let's go through this together. So the something in a circuit is a measure of how much something is flowing. So it's going to be, of course, the current in a circuit is a measure of how much charge is flowing. Okay, current is measured in amps from the French physicist Ampere. A higher current means more charge is flowing past a point every second. Because remember, I equals Q divided by T. And a current of 1 amp equals 1 coulomb, the French physicist, of charge flowing past a point every second. The total current entering a junction must equal the total current leaving, if that's exiting, I guess, exiting a junction. So let's see what we've got. So we've got second, we've got current, we've got equal, we've got junction, we've got charge, electricity. Oh, okay. So I guess, see there, instead of charge, it will be electricity. Okay, so electricity, exiting amps and coulomb. So we are all done for this lesson. So the next lesson will be moving on to the voltage, which we've already kind of introduced in the static electricity unit.